So let's take a look at some of the other screens that popped up when we enabled the multi-plot main screen. One of them that you may have noticed came up is the multi-plot reference star settings. What this screen is an indication of which comp stars are currently selected, as well as, of course, what the target is. In this case, is T1. What we can use this screen for is to deselect comp stars that we believe are either variable or have a lot of scatter to them. So for example, as you recall, when we were plotting comp star C5, we did see it had a lot of scatter to it. So let's go ahead and deselect comp star 5. And let's then also take it out of any of the future plotting, so we won't be checking it. And furthermore, you see that the plot under Y data, the multi-plot Y data screen, the value for this item has changed from relative flux C5 to T5, namely AstroImageJ has taken it out of the set of comp stars, and in fact the value for comp star C5 is no longer used in computing the relative flux of T1. So let's go ahead and include in the graphs the following values: the relative flux of T1, the relative flux of the 3 remaining comp stars. And in fact, let's separate out the comp stars, and we can do that by moving and shifting their plots. If we go all the way to the last part of the multi-plot Y data screen, and what we can do then is, for example, move C3 down a bit, and we can move C4 down a bit. So we have the comp stars then underneath each other. Let's go ahead and also plot the relative flux of T1 as a transit fit. And we'll do that by selecting the second data set. As you recall, that data set had as its fit mode the bucket-shaped icon, which indicates that to AstroImageJ that it will attempt to fit a transit model to it. Now, let's take a look at how that's actually done. This is probably one of the more important steps when we're actually trying to refine the ephemeris of known exoplanets. For candidate exoplanets, it's probably not necessary to actually do a transit fit, since we don't know much more about that exoplanet. We're just trying to see if there is a nice bucket-shaped curve. But for known exoplanets, we can actually now try to fit a transit model to it. And the way we do that is through the dataset 2 fitting screen that you see here. And let's now take a look at some of the input parameters to it. And these are obtained from the worksheet. So if you pull out the worksheet, we'll start filling in some of these values if they're not already here. So for period, from the worksheet, you see that the period for WASP 12 is 1.0914. Let's go ahead and change that to the appropriate value for WASP 12. The value that was previously here was from a previous plot. We also want to change the various parameters of the host star, and in particular, we want to set the radius of the host star, which is in units relative to our sun. And from the worksheet, you see that that's 1.63. So let's go ahead and change that to 1.63. Now, one thing that you'll see here is the relationship between the spectral type, the effective temperature, and the radius of the sun. The radius of the host star. And there is a well-known relationship among those different parameters. So as we change one, we change the other. The value for R star in AstroImageJ does not affect the fit of the model to our observational data, but more it's used to compute and to estimate the radius of the planet itself, RP. And one of the output parameters of AstroImageJ is the value RP over R star squared, namely the depth of the transit. So R star is used simply to compute RP. It's not really used in doing the model fit. More what happens is that the model fit produces this ratio squared. Okay, so we set the period, we set R star. The other values as inputs or as so-called priors to the model fit are the limb darkening coefficients U1 and U2. And again, looking at our worksheet for a V filter for this particular exoplanet, we've determined that the limb darkening coefficients for U1 would be 0.39056081, and for U2 would be 0.30269992. The check marks under the lock column indicate to AstroImageJ that for these two particular parameters, we're going to lock them as input so that you see that they're carried over in the best fit column. So we're forcing AstroImageJ to use these as input parameters. Okay, so we have some initial results of the fit, but now let's take a look at how to optimize and refine them. The parameters that AstroImageJ uses to refine the fits are the so-called D-trend parameters. One of the more common ones is air mass. And air mass takes care of any air mass that the transit is going through, that is to say, during the duration of the transit, the air mass is experiencing. That adjustments then are made to compensate for the particular air mass that that particular host star is going through as it's transiting, let's say, for example, from halfway up the horizon all the way to zenith. Now, the way that we determine which D-trend parameters to check here, and these are the more common ones that are indicated, by the way, here. One can change whatever D-trend parameter wants, but air mass is one of the more common ones. And the way that we know whether or not a D-trend parameter should be changed is to look at this particular statistical measure called BIC. And if BIC is reduced by more than 2 units, then that tells us that that D-trend parameter is probably worth using. So let's go ahead and click on air mass and see what happens to BIC. And BIC changes to 487. So indeed, air mass is probably a good D-trend parameter to use in this case. Okay. Now we can go through and try other D-trend parameters, but for the purposes here, let's just select air mass as D-trend parameter we're going to use. Some other important values here, you see that the RMS, which are the residuals that the model has calculated relative to the observational data, looks pretty good, is 0.003721. Now let's go back and look at our plot, where we are with our plots. You see that the transit model fit looks pretty good through our observational data. Now, one other thing we can do on the screen is to show the residuals of our fit for each of the data points. That's to say, the difference between the actual observations for each data point and the model fit. And we do that by checking this box called Show Residuals. And if you take a look at the plot, you'll see what's happened when we check that box. So when we check it, this line appears. Let's move this screen out of the way. That shows the residuals of the transit model relative to our observational data. Now, to make this a little bit clearer, let's adjust some things on the screen here. And let's do that by going to our plotting screen, and let's go all the way to the far end. And what we're going to do is we're going to shift some of these curves upwards. So for example, let's shift up the relative flux curve. Just going to shift it up a little bit. Let's shift up the transit model curve just so we can see the residuals a little bit better. Okay, and then we have some room here to shift the residual values down. And we do that by going back to our data set fitting screen. And we see here this option called shift. Let's shift that curve down a bit so it's underneath our transit model. And there we go. So what we see then is the raw flux, relative flux of T1. Whoops. Again, let's take a look at a better view here. I'm going to redraw our plots. There we go. So our transit model, our residuals, and these are our CompStar plots. Now to pretty up the CompStar plots a little bit, let's go ahead and scale them a little bit better. And we do that by going to our multi-plot Y data screen. And we're going to, let's scale the CompStar plots to 0.5 just to make them a little bit easier to see. Okay, there we go. So here are our CompStar plot screens. Okay, and lastly now, if we wanted to put error bars around each of our observational measurements, we can do that by going back to the data set fitting screen. And this option here, show error, we'll click on that. And if you watch the residual graph here, you'll see that there are error bars that appear. Okay, so there we go. So we have completed our observational analysis of WASP 12. And the key thing now, of course, is what the model fit finally looks at. And the key parameters in the model fit are, first of all, the squared ratio of the planet to radius of the planet to the radius of its host star. And you see that as 0.01309. The ratio of the semi-major axis to the orbit of the planet to the radius of the host star is 3.22. The midpoint of our transit for this observation is the BJD TDB time you see here, and the inclination you see here of the orbit. So these parameters are the ones that AstroImageJ has determined from the model fit that we have performed. And if you then compare the value of the midpoint here, 0.601099, with the predicted midpoint, if you go to the spreadsheet, you'll see that a previous run of AstroImageJ came up with a midpoint of 0.60123. Here we have 0.60109, and that's simply because of some minor changes in some of the parameters we made, but nevertheless very close to the previous run that we made. You'll see that it's very, very close to the predicted midpoint of 0.6019, and in fact we're within a minute or less. So we've got a very good observation here, very close to predicted times. So that concludes our analysis of this particular example. I would refer you to the guide on the astrodentist.com website for more details as to various options for taking care of things like meridian flips, alignment of images, and other options for actually taking some of the AstroImageJ data as output for either other programs or to the professional community who might want some of this data for their own use. So that concludes then our observation analysis, and we'll proceed on now to the next module.